Let's see how we will prove this by induction again, right? So this theorem says that if you have no graph on n vertices with no complete graph on m plus 1 vertices as a subgraph, then this is the number of edges it has. Okay, base cases are done. Okay, so then what do you do? So you have a graph on n vertices. What do you delete? What did we do for Mantle's theorem? We deleted an edge, right? So what do you think you should do here? Pick n vertices is given. M vertices, okay. I don't have a choice. I'm given a graph. See, this is exactly what I said when I started off with mistake induction on induction people do. I am given a graph on n vertices with no km plus 1. So you have to use that somehow, right? That's what we did in our thing. We said, okay, I'll given a graph, I'll find an edge and delete it, both endpoints. If there is no edge at all, you are already done. Yeah. We can take a click of size m outside. Why should there be such a click? Very good. So first let's look at a graph with no km plus 1 with maximum number of edges. Okay. Consider such a graph and we will prove an upper bound for that. Then it follows that for any other graph, such an upper bound will follow. So first thing what you do is argue that such a graph has a click on m vertices. Why not? Because you will be able to add more edges and you will get a click on m vertices. So first find a click on m vertices and delete it. Then the job is done. Then there is nothing more, right? So always the first starting point is where you have to be careful. After that, what you have to do is more or less clear, right? What you have to do is consider a graph on n plus 1 vertices with no km plus 1 maximum number of edges. It must have a km, delete that. Now the remaining graph has n plus 1 minus m vertices, no complete graph on m plus 1. So you can apply induction hypothesis on that. Now your km, what can you say about the remaining graph? Each of the remaining n plus 1 minus m vertices is adjacent to at most m minus 1 vertices of the km, right? Because any single vertex, if it is adjacent to all of it, that will form a km plus 1. So any single vertex is adjacent to at most m minus 1 of the click you have deleted. Now you do your calculations and things will fall in place. So we removed a km. Then this is the remaining graph n plus 1 minus m vertices. So here we have a bound, whatever that bound is. I forgot what that bound is. This minus this many edges inside here. And then for each vertex here is adjacent to at most m minus 1 of them. So you will add n plus 1 minus m into m minus 1. This is the total number of edges plus edges inside km. That's m into m minus 1 by 2. And if you add them all, your induction thing will fall in place. Okay, here's another nice proof. Okay. So what we will show is that an extremal graph, a graph with the maximum number of, so this is proof number 2. Maximum number of edges among graphs with no km plus 1. First we will show that it's a complete M-partite graph and each part has at most equal number of edges. Okay, we're going to no induction. We're going to try this a different proof. Okay, very nice proof here. So again, I think we argued for bipartite. If I manage to show that it is a complete some partite graph, then the maximum number of edges is obtained when they are all of equal size. Otherwise, you can move one small from larger to smaller and you will get more number of edges. So if I show that it will be a complete M-partite graph, the maximum number of edges you will get is when they are all of same size and the bound will follow. Okay, so we will focus on proving the first part. And the way we were going to show it is the following. What we will show is that, so you have a graph, extremal graph with maximum number of edges. What I will show is that the non-adjacency relation, okay, let's relate a pair of vertices if they are non-adjacent. Okay, is it a symmetric relation? Yes, if A is not adjacent to B, B is not adjacent to A. Is it a transitive relation? If A is not adjacent to B, B is not adjacent to C, I don't know about A and C are adjacent or not. We will actually show that in such an extremal graph, the relation is transitive. Okay, that is the rest of the proof. Okay, so we'll show that the non-adjacency relation is actually a transitive relation and hence an equivalence relation. So you can break your entire vertex set into equivalence classes, and each equivalence class is an independent set, and there is an edge between everything else, because if you have a non-adjacency between two parts, you can pull them out. Right? Equivalence classes means that all of these guys behave the same way. So they are independent and they are complete edges across. Okay? So all we will show is that in such an extremal graph, this non-adjacency relation is a transitive relation. Then we can break the vertices into equivalence classes of independent sets, showing that the graph is a complete R-partite graph for some R. Now, so clearly R is, sorry, it's not 2, it should be R. Since there is no k m plus 1, you can't have m plus 1 parts or more. So the number of partite sets will be at most m, and we will show it's actually equal to m, because if it is less than m, then you just break it up and create one more and you'll have more edges out of it. It's easy to show. Okay. So our focus is now in trying to show this part, that if that this non-adjacency relation is a transitive relation in such an extremal graph. Okay, I just not 3-line but maybe 6-line proof. Okay, so let's start. Suppose you have a pair of, xy is a non-edge, yz is a non-edge. Suppose xz is an edge. There are two cases. So xy is non-edge, yz is non-edge, and xz is an edge. Suppose degree of y, the middle vertex, is strictly smaller than the max of the degree of these two guys. Then I would argue the following: remove y and replace it by whichever x or z which has the higher degree. What does replace it mean? I just use the neighbors of whatever that x and z and do it for my y. So delete y and add a copy of the vertex x or z, the one with the higher degree with the same neighborhood. Let me just again, I think calls for a picture. So the situation we have is that xy is non-edge, yz is non-edge, but xz is an edge. Okay, and degree of y is strictly less than max of degree of x and degree of z. Now what I am going to do is construct the same graph. Now let's say, without loss of generality, z has the higher degree. Okay, then what we will do is x, instead of y I will have z prime and z. Basically y is playing the role of z, which means it has the same neighborhoods. So what are the neighborhoods? Since z is adjacent to x, z prime will also be adjacent to x, and whatever z's neighbors here are, the z prime will have the same neighbors. I have a new graph now. Okay, so I want to prove two things: that this new graph has more number of edges, and it also does not have a complete graph on m plus 1 vertices. Right? It has more number of edges is clear, right? Because degree of z is strictly more than degree of y. I removed y and added a higher degree vertex and added more edges. Okay, it also cannot have a complete subgraph on k m plus 1, because how will it have? If z prime, with z prime, if you have 1, then you should have had 1 with z also, because z prime is actually a twin of z. Okay, so is it clear that I have a new graph with more number of edges and still it does not have a complete subgraph on m plus 1 vertices? So it contradicts the fact that I am looking at a maximum graph with maximum number of edges. So this is case 1. So all I am saying is just delete y and replace it by x or z. Case 2, degree of y is greater than or equal to degree of x and z. What am I going to do? I am going to remove x and z and replace it by copies of y. Here also now we can argue that this also does not have a km plus 1, but it has more number. Let's count the number of edges. Maybe it's better to do it in picture. So in the other case, degree of y is greater than or equal to degree of x and degree of z. So I have this situation I'm going to replace both x and z by, let's say, some y prime and y double prime, which means that whatever y's neighborhoods are, right, the same guys y prime and y, these two guys will also have. Clearly, it does not have a km plus 1 now, because if it must be using one of these two new vertices if there is, but then I could have had the same thing with using y. So, this also is a graph which does not have a complete subgraph on m plus 1 vertices. Now, it has more number of edges. Why? Because degree of x was strictly less, degree of z was strictly less, sorry, not strictly, less than or equal to, but now I have replaced with something larger for both of them. Okay. So, there is a little calculation you can do to show that number of edges now is you got your degree of x plus degree of z minus the one edges which are gone, that is gone, but it is replaced by degree of y. You can show that the number of edges now is more. Okay. To summarize, what did we show? We wanted to show that the maximum number of edges in a graph with no km plus 1 is blah blah blah, and what we said, the non-adjacency relation in the extremal graph is an equivalence relation. So, such an extremal graph must be a complete M-partite graph. Okay, so these are just very cute proofs. It just, yeah, okay. Now, finally, I will give one proof which is a bit of an algorithmic randomization probabilistic kind of a proof, and then we will conclude. Okay, so for the same, so what we will show is the following, slightly different phrasing of the same theorem. If you have a graph on n vertices with no independent set on m plus 1 vertices, then the number of edges in the graph is at least something, right. Basically, you take your graph and look at the complement, and you are arguing something about the complement, because if the graph does not have k m plus 1, the complement will not have an independent set on m plus 1, and if the graph has at most this many edges, the complement will have at least this many edges. Okay. So, I am going to prove it for the complement. So, we will assume that my undirected graph on n vertices with no independent set on m plus 1 vertices, what I am going to do is, here is the following is an algorithm, a greedy algorithm to find a large independent set in the graph. Okay. So, what is a greedy algorithm to find a large independent set in the graph? I will take the first vertex in my independent set. Basically, let us consider some arbitrary ordering of the vertices. Take the first vertex into an independent set, and you just scan through the vertices and see if you can take it, take it. That is it, right. What does it mean by if you can take it, take it? Look at a new vertex. If it is non-adjacent to whatever I have collected, I will add it, otherwise I won't add it. It's a very simple greedy algorithm to find some independent set. May or may not give you a good independent set, but whatever it is. So here is so start with an empty set. If no neighbor of I is in the independent set, then I am going to add I into my solution, and that is the independent set. And I want to understand the expected cardinality of the independent set. Okay. So, this is a, what do you mean by expected? Where the expectation is over all n orderings of the vertices. Okay. Now, this is a subtle, probably new concept for you, right. So, let's just go back. When somebody said in the morning that quick sort is n log n on the average, right. What does it mean? When you say average, you are talking about a distribution, right. You can talk about average of 50 students' marks, right. When you say average, you are talking about a distribution, it is not one thing. So, the quick sort average number of comparisons is n log n means what? Average or what? Arrangements of the input. See, how is quick sort sorting? It picks pair of elements and it compares, right. So, if this number is 50 and this number is 70, or if this number is 5 and this number is 7, the answer is going to be the same, right. So, they are all in some sense all possible inputs. You can break it up into equivalence classes. What are these equivalence clauses? All possible orderings of the input, right. It is just all possible orderings of the input so how many possible orderings are there? No. Of n input, how many possible arrangements are there? N factorial, right? So n factorial permutations. You take your input because quicksort looks at two elements and compares whether this is less than or greater than. So if it is, for example, already sorted, then it doesn't do very well. So if you do all possible n factorial permutations, for each permutation count the number of comparisons and take the average over them. That average is what is n log n, even though for some permutation it may be n square. Okay, that's what it means. So this is very important to understand it. So similarly, what I want to argue here is, I have an arbitrary ordering of the vertices and this algorithm produces an independent set. I want to understand the average size of the independent set, where the average is over all possible permutations of the input. Okay. Now, we will get to, when we get to randomized algorithms next week, we will do more of it, but this is simple enough that we can do it. So, here is one way to analyze this expected size of this cardinality, is that I run through every vertex and see what is the probability that that vertex will be in my independent set. Okay. Probability is over again all possible permutations. Whenever you talk about probability, average, you are talking about distribution. So, what I am saying is, over all permutations, what is the probability that my vertex I is in the independent set? Okay, it sounds hard, subtle, but there is a very simple argument, we will get there. Probability that vertex I is in the independent set is clearly the probability that if you look at I and its neighbors, if this is the first vertex, then it will definitely be in the ordering. In the ordering of the vertices, there are all possible orderings. If you look at a vertex, in that ordering, among itself and its neighbors, if this is the first vertex, it will be definitely in. Right? So that probability is at least the probability that I comes first among its neighbors in the order. What is the probability that I comes first among the order? Intuitively, how many vertices are there we are looking at? Suppose di is the degree of vertex I. We are looking at di plus 1 vertices. Out of this di plus 1 vertices, there are di plus 1 factorial permutations. And what is the probability that my vertex I is in the first vertex? You can see that it is at least 1 by di plus 1. Okay. All this requires proof. Okay. One can run through all permutations, carefully do some combinatorics counting and choose something and see how many permutations and all that. You can prove this. Okay. So, my expected size of the cardinality of the independent set, which I get by this greedy algorithm, is actually I should have a greater than or equal to here, because of this probabilities are greater than or equal to summation 1 by di plus 1, where di is the degree of the vertex I. Okay. Again, by some inequality, this is minimized if all the degrees are equal. We know that summation di is 2q. So, if 2q by n is the average degree, that is when this inequality is maximum. So, this is maximized when all these degrees are equal, which is 2q by n. So, the expected size of the independent set is at least summation 1 by 2q by n plus 1. If you simplify, it becomes n square by 2q plus n. Okay. In the process, I am sure we forgot what we wanted to prove, right? We got into something, right? So, what did we want to prove? That I have a graph which does not have a large independent set, and I want to give some bound on the number of edges in the graph, right? Now, what I did, I just ran some greedy algorithm and argued that the expected size of the independent set it's going to produce is at least this much, okay? Which means that the graph should have an independent set of size at least this much, right? Is it clear? If the average mark in the class is at least 75, there must be somebody with score at least 75. If everybody is less than 75, how can the average be greater than or equal to 75, right? This is exactly saying that. Suppose the average size of the independent set produced by the algorithm is at least this much. There must be some independent set in the graph whose size is at least this much, okay? But we know that the graph has no large independent set, right? So, n square by This is a lower bound on the size of the independent set, but I know that this cannot be greater than or equal to m plus 1 because my graph has no independent set of size m plus 1. Now, from here you simplify when you get q is at most this much. So, this is an algorithm, argument using some probabilistic method, greedy algorithm, do some expectation, and from there you argue that there is one of size this much, but the graph does not have an independent set of size m plus 1. So, this number is at most m, and do some simplification, you get this. Okay, so we have seen proof by induction. We have seen proof by pick a large independent set and doing some calculation, some weights being distributed on the edges from vertices. We have seen proof by probabilistic arguments. Okay, so that's the goal. Just to want to give you a flavor, a variety of proofs.